A plane does not need to lose GPS to be in trouble. The more dangerous version is quieter, the screen still looks normal. The receiver still shows a position. The route still moves. The cockpit still has numbers. But the signal underneath those numbers may be false. That is why spoofing feels so dangerous. It does not announce itself as failure. It can look like confidence. GPS is part of a wider GNSS layer: satellites, clocks, ground control, receivers, and timing services. Most people see it as a blue dot. Aviation, shipping, telecom, power grids, and finance see it as infrastructure. The basic problem is physics. Satellite navigation signals arrive at Earth extremely weak. A receiver can separate them from noise because the timing pattern is predictable. That elegance is also why interference matters. Jamming is simple: drown out the signal so the receiver cannot hear it. Spoofing is worse in a different way: feed the receiver a believable false signal, so it calculates a false position, altitude, or time. The FAA now publishes a dedicated GNSS interference guide. IATA's Safety Risk Assessment says participating airline data recorded more than 1 million GPS signal loss events from 2021 through mid-2025. EASA and IATA say reported GPS signal loss events rose 220% from 2021 to 2024. OPSGROUP's spoofing workgroup described a wave that grew from hundreds of affected flights per day to roughly 1,500. That is why the official documents read less like theory and more like a checklist. The FAA guide focuses on symptoms, system impacts, reporting, training, and recovery. The important shift is this: pilots and operators are no longer treating GNSS interference as a rare technical footnote. This does not mean aircraft simply fall out of the sky. The danger is workload. Warnings can appear. Navigation accuracy can degrade. Procedures can become unavailable. One system can feed bad timing or position to another. Crews may need ATC help, conventional procedures, or a diversion. The safest response is not to improvise around a broken map. It is to fall back to approved procedures, cross-check raw data, compare instruments, use ground aids where available, and tell air traffic control early. In other words, the modern cockpit still needs an older discipline underneath it. One ugly detail is that spoofing can contaminate navigation systems even after the aircraft leaves the bad area. A normal signal returning does not always mean every downstream system instantly recovers. At sea, GPS is tied to bridge navigation, timing, communications, and AIS. Merit warns that interference and AIS spoofing have been reported globally. A ship may not be lost, but its displayed truth can be degraded. AIS makes this more complicated. It is useful because ships broadcast identity, position, course, and speed. But it is also open and not cryptographically protected in the way people imagine. When position data becomes wrong or spoofed, the bridge display can become a confidence trap. Why is this getting louder now? Conflict zones use electronic warfare to counter drones, missiles, and surveillance. But radio interference does not respect a neat line on a map. It can spill into civilian routes nearby. There is another trap: not every GNSS problem is a hostile attack. Testing, equipment faults, local repeaters, spectrum conflicts, and space weather can all disturb signals. The point is resilience, not panic. The blue dot gets the attention, but timing may be the deeper dependency. GPS time helps networks synchronize. It supports telecom, power systems, data centers, financial timestamps, and other quiet services that need precise clocks. When timing is wrong, the failure can look like a network issue, a market data problem, or a local equipment fault. This is why CISA and NIST frame positioning, navigation, and timing as critical infrastructure. A map error is visible. A timing error can hide inside logs, transactions, communication links, and control systems until two systems disagree about what time it is. The answer is not one magic secure GPS patch. It is layers, inertial systems, ground navigation aids, multi-constellation receivers, authenticated signals, monitoring, better reporting, and operators trained to notice when the map is too perfect. Resilience means assuming the signal can fail before it actually does. That is why the official guidance sounds practical, not cinematic. Cross-check instruments. Tell air traffic control. Use approved procedures. Report interference. Keep conventional navigation and timing fallbacks alive. Modern navigation is becoming more resistant, and new authentication tools are coming online. But a stronger signal does not remove the need for backups. The future is not GPS or no GPS. It is trusted PNT, with failure assumed. So the question is not whether GPS works. Most of the time, it does. The question is whether our systems can tell the difference between a good signal, no signal, and a lie that looks just good enough.